So in the last video we talked about modeling a discrete time model with one variable, and the result of that simulation was a plot looked like exponential growth. And if we look at the plot, it looks something like the following. We did this in MATLAB, and as you recall, we had x sub 1 equals 2. That was our initial condition, our starting value for x at time equals 1. And x sub t equals 1.1 times x sub t minus 1. So that 1.1, that was our growth rate that we chose for the model. Now I want to illustrate here that you could actually rewrite this right-hand side in the following format. You could rewrite the right-hand side as 1 times x sub t minus 1. And 1 times x sub t minus 1, that's kind of silly. Why even write the 1 there? But you'll see why I wrote it there in a minute. Plus 0.1 times an x sub t minus 1. And so essentially what you've got is on the right hand side, you've got x sub t minus 1 plus 10% growth. And let's write this down. So this is our previous amount, say from last year or last month. So this is our previous value for x at time t, and then we're going to add on some new amount. So this is an additional new amount. So that's like our growth. It's growing by 10%. Okay. We're going to change this up just a little bit. Not all populations or not all bank accounts or whatever you're modeling grow with this exponential growth model, right? This is unbounded growth, and this is not always realistic. So let's make a note of that. Unbounded, because this grows up, it goes to infinity, right? This is unbounded growth. Okay, so I'd like to take a look at two definitions. We've got the definition of carrying capacity and a definition of the discrete logistic model. So the carrying capacity is the maximum population size an environment can support indefinitely with given resources. And the discrete logistic model incorporates carrying capacity into the population growth model. And as we said, this is a discrete time model. Okay, so let's take a look at what we've got here. We've got x sub t equals x sub t minus 1 plus r times x sub t minus 1 times parentheses 1 minus x sub t minus 1 over k close parentheses. This first term is our current population. So x sub t is the current population. We'll call it current pop. X sub t minus 1 is our old population. We'll call this old pop. And we've got our old population, and we're going to add to that some new amount. Okay, so to get the current population, we take our old population, we add some new amount to it. Now, this new amount comes to us as a product of a couple of different things. We've got r in here, we've got x sub t minus 1, and then we've got this other carrying capacity factor. So r is our growth rate, and if that's positive, we're going to be adding. If it's negative, we are going to be decreasing. We've got x sub t minus 1, that's the old population. And then on the end here, we've got 1 minus x sub t minus 1 over k. Notice that when x sub t minus 1 approaches k, which is our carrying capacity, 1 minus x sub t minus 1 over k approaches 0. Right? When x sub t minus 1 approaches k, that last term is 1, so 1 minus 1 is getting close to 0. And on the other hand, when x sub t minus 1 is 0, or very close to 0, then this last term, this factor 1 minus x sub t minus 1 over k, that's getting really close to 1. And so we're adding in here our new amount. It's very much like the exponential growth model we saw in the previous example. So this is a really nice model. As we said, K is our carrying capacity, R is the growth rate. It's a really nice model because we do see real-world populations kind of fitting this paradigm. On the horizontal axis, I've got t, and on the vertical axis, I've got x of t.